Okay, hi, we are group 6 and our topic is about isospectralization. Okay, so um, it's no, yeah. So here's the outlines of the presentation. So we will go through, like, introduce the topic, and then I'm not controlling. Yeah, and then we will give a formulation about the problem, and then we talk about the implementation, about the models, and then we talk about the results, and finally we will discuss some future work. Okay, so let me start. So the idea of isospectralization is that whether we can discuss in the problem that whether we can recover the shape of a geometric object from its Laplacian spectrum. So this is a classical problem in spectral geometry, and it is actually theoretically negative. And because there exist isospectral manifolds that are not non-isometric. So, but in practice, little is known about whether this can be, at this, like, estimate the shape, rather than like reconstruct perfectly. So in this paper, they try to formulate this problem that the spectrum alignment, which they call isospectralization, as a numerical optimization procedure. And so in this way, they can apply modern differentiable programming tools like PyTorch or TensorFlow for numerical optimization. And they propose several regularizers for this task, and they demonstrate that the proposed method actually can work for flat shapes and surface. And they also show some applications to style transfer and non-isometric shape matching. Yeah, so first is the formulation and the notation. So in this project, we only talk about the discrete case that an x equal to VEF. So V is the vertex and E is the edges and F is the faces. So we only discuss the triangular mesh. And so the bold V stands for an embedding of the shape. So it's the coordinates for all the vertex. And then we can compute the cotangent Laplacian defined on this embedding for that shape. And we use lambda to represent the eigenvalue sequence of the Laplacian. So this is the spectrum. So lambda 1 to lambda n is from the smallest eigenvalue to the largest eigenvalue. Okay, so the goal, in this way, they can formulate the problem as like, we want to find the optimal embedding that aligns the spectrum to a fixed spectrum, a fixed given eigenvalue sequence. So we can see the formulation here is an optimization problem that you want to minimize over the shape embedding. So find the best coordinates for the different vertices that you can align the eigenvalues of the Laplacian to a target eigenvalue sequence. So mu is given, and we want to make the shape embedding that has the same spectrum to the eigenvalue sequence. So we use a weighted norm that focuses more on the low frequency parts for this to like a metric on how this spectrum alignment works. And we will have a regularization term. So actually, yeah, so here's the notation we will use for the regularizers. And so VI denotes the positions of vertex, and Lij is the length of edge Eij, and Aijk is the area. Okay, so they actually propose several regularizers for plate shapes and general surface. So here's the regularizer they propose for flat shapes. So the first regularizer, it actually encouraged smaller boundary edge lengths. So you can see it's the sum of all the edge lengths for the boundary edges. So this is actually the boundary length. And the second regularizer, it penalized the triangle flips. So the formula looks like this. So you can see the rotation matrix. So whenever the triangle flips, then it will get a negative turn and it will be penalized. And the third regularizer, it encouraged small variance on the triangle areas. So it actually encouraged the triangle size to be equal. So we will have a evenly sampled meshes. And so the term is actually just the calculate the variance of the triangular areas. And the final regularizer for flat shapes is the L2 loads on all the edge lengths for the interior edges. So it encourages more interior edge lengths. So it has the effect of encouraging, again, evenly sample mesh. So here are the regularizers they propose for general surface. And the first regularizer encouraged the vertex to lie close to the very center of their one ring neighbors. So you can see the figure at the right. We want this VJ to be at the center of its neighbors. So this can be formulated as a regularizers that compute the metric product between the initial graph Laplacian. So this doesn't change at all because it's graph Laplacian, not the cotangent Laplacian, and times the vertex embedding. And we take the norm square. And the second regularizer is it estimates the shape volume. So in this way, by setting the positive or negative term for this one, we can actually control during the optimization, we encourage the volume to grow or to shrink. So this way we can disambiguate isometric shapes that have different volumes. And the third regularizer encouraged the vertex to lie close to the very center. So this time it used the cotangent Laplacian. So this one doesn't present in the paper, but actually we found that in the implementation, they actually have two similar terms on using different Laplacian. And the final regularizer, it encouraged small total displacement from the initial embedding. So like we know the problem is formulated as an optimization problem. So we have an initial embedding. So we doesn't want the final output as a like very different from the initial embedding. So this is generally calculating how different from the initial embedding to the current embedding. And it's weighted by the triangular size. So these are the regularizer they propose. So together with the main objective, which is the spectrum alignment. So they propose different regularizers for different scenarios or different 2D shapes and 3D shapes. So together, this is the whole objective functions.
Okay, so in the following slides, I'm going to talk about the implementation details and the experimental results we have done. Okay, so we use modern auto differentiation APIs for numerical optimization. So in particular, the authors have provided their implementation using TensorFlow. And the first thing we have done is to implement the algorithm using PyTorch. And then we will show many experimental results on the shape reconstruction using our code. So the first one I want to show is for 2D shape reconstruction. And we optimize the vertices in the initial shape with respect to the weighted norm of the difference between the initial and the target spectrum, and with its corresponding regularizers. And here we demonstrate the reconstruction results from oval to Mickey Mouse and the bell shape. We can observe that the optimization makes the reconstruction shape become more close to the target shape after 2,000 iterations. We also visualize the eigenvalues to make sure the values actually become closer to the target one. So the initial eigenvalues is plotted in the gray line. The target eigenvalue is plotted in the red line. So our final reconstructed eigenvalues have become close to the target ones. And we also plot the loss training, the training curve for our loss values. Notice that the training process is not quite smooth. It's because the spikes is result from some triangle flips happening during the training process. But after the training process, the loss value reached the global minimum. Next, we want to show our results on 3D shape reconstruction. And here we reconstruct the shape from the cube to the cube with a knob as the target shape. And in this case, we can successfully reconstruct the global appearance. We also visualize the eigenvalues plot and also the loss plot for training process. And the curve is smoother than the flat shape case and can finally reach the global minimum. And notice that the volume regularization term does matters the reconstruction results. So as you can see the red circle here, in this row, we use small weight on our volume regularizer. So, but in the first row, we use the larger number. And this regularizer actually can help the reconstruction process to make the shape expand to the target shape. And next, we want to show the results from ShapeNet reconstruction. So here we demonstrate two examples. First one is that we initialize from a sphere shape and we want to graduate reconstruct to a target shape like this is a can. And the second one is starting from the cube and we want to adapt to the bottle as a target shape. Because the vertex distribution is quite not uniformly sampled. So basically it violates the assumption we used in our regularization terms. So we can expect the reconstruction results might not be very accurate, but we can also observe that the global shape become like a rock-like shape, which is close to our target shape. And for the second example, the points actually become degenerate to its centroid, and the points slightly move upward, which is close to our target shape. The vertex are actually densely distributed in the upper part of the shape. And finally, we want to show the style transfer task on ShapeNet objects. So basically, we choose two shapes within one category. And in the first two rows, we choose two pairs of balls. And as you can see in the first row, the target shape does not have uniform sampled vertices compared with the second row. So the result for the first row is not so accurate. But if you can observe that in the second row, because the source and target shape follows the assumption for uniformly sampled vertices, and we can obtain the more successful reconstruction results. We also tried our algorithm on more complicated shapes. Like in the third row, we use desktop, two different desktops, but for the shapes, the distribution of the vertex is not quite uniform sampled. So the reconstruction results are gradually degenerate to the centroid.
So in summary, we noticed that on simple shapes, isospectralization successfully replicates the shape of an object by its Laplacian spectrum. So simple shapes were like on the flat shapes, and as well as some of the like the sphere with the little knob at the end. And another thing we noticed is that this technique also allows us a correspondence-free way to transfer style, as we saw with in the previous slide, this bowl. So now we're gonna talk about our future work. One of the future works that we would like to get done is shape matching, which is using our algorithm, deform a shape X to X prime with a target of Y. So in this case, it would be horse would be X and camel would be Y. And we would deform X to an X prime with our algorithm with the target of camel. And now we could run our functional map algorithm and compare the matches between X and Y, X being the undeformed shape, and X prime and Y, X prime being the deformed shape. And we expect that X prime X prime will match better to Y than the initial X. And here is just a picture of that case. So some issues we faced with shape matching though were, so we wanted to investigate the false data set because that was what was initially implemented in the paper. However, an issue we hit was the fact that the false data set is incredibly large. And so we would need to investigate a remeshing technique so that we could run it through on our computational limitations. Another issue we faced was the open source functional map code or algorithms required a separate pre-processing step, which you calculate shot descriptors for an object. So while we were able to run the algorithm on its own with their sample data, it was difficult to calculate shot descriptors for our modified data after we ran it through our algorithm. So here is an example of what the paper implemented on the Faust dataset and what we wanted to implement. As we can see, there is an original X and then an X prime, which is deformed to look like target Y. And then you would run the shape matching algorithm between X prime and Y. And as you can see, there is a more diagonal functional map of matrices, which led to better conditioning for shape matching algorithms. So other future work we would like to explore is a choice of regularizer. As we saw with ShapeNet, different ways of meshing it where like smooth surfaces are more loosely meshed cause degenerate shapes to appear. We would like to investigate potential regularizers that would allow those kinds of meshings and still provide good results. Another thing we noticed was hyperparameter choice. As we saw before as well, with the cube with the knob, if we pick too low of a hyperparameter, it would result in it not actually converging to the shape that we wanted. given more time, we would like to explore the optimal hyperparameters for a given shape. And then another interesting application could be shape interpolation. As you can see from this image, like given a tiger on the left and a horse on the right, we would like to be able to see it transfer its like shape to X to Y. And this has useful applications in real field work, such as like an animator. Now you could have an animator only create keyframes and then use an algorithm to interpolate between those, saving a lot of development time. Here are the references. So the former is the paper which we implemented. The latter is where we got the image of shape interpolation. Thanks for listening to our presentation.